Okay. So welcome, everyone. This is the first, it's sort of the launch event for Vulkan. We have had the spec live in public for a while, but this is the first time we've spoken about it in public as Khronos. I'm really excited about that. I'm delighted that so many people are here and are interested. We have an incredibly, scarily full agenda. The talks are broken into basically 4 sections. There's a little bit of big picture stuff from me. I should have said, my name's Tom Olson. I'm chair of the working group. I'll talk a little bit about where we came from and the status of the API in the public domain. One of our senior spec editors, Jeff Boltz, will talk about the philosophy, design philosophy of Vulkan. And then we'll go into some deep dives from members of the working group, talking in detail about how parts of the API work and how they're intended to be used. Notice there is no gentle introduction. There's no broad overview. The spec's been out for a month, and we kind of assume you know the basics. So we're going to dive right in and go as deep as we have time for today. So that's the first quite a bit. That's 2.5 hours. After that, we have 2 of the real rock star game developers who are members of the group and who contributed a lot to the Vulkan spec, Dan Baker and Dan Ginsberg. We have, by the way, 5 Daniels in the group. It's kind of a problem when we're doing phone calls. But anyway, they will come and talk about their experiences using Vulkan in AAA engines. And then we have, in the last hour, 4 presentations. The first 2, I think, are really cool. They're open source projects that have taken Vulkan on. They got early access somehow and have been doing some interesting things and showing that it's not just for AAA engines. You can do cool stuff with it, even in a relatively small-scale project. And then at the end, we have a party, food, drink. That'll move in here because the back room is too small at 7 o'clock. A little bit of logistics. Notice that there were no breaks. Sorry about that. We had too much content. If you need to get some coffee or you need to get rid of some coffee, your best bet is to wait for a Q&A between talks. You go out and turn right. If you go all the way back, straight back, you end up where the coffee and the water are. And if you go back and turn right at the elevators, that's where the restrooms are. They're key protected, so you need to enter 3636. Remember that number. The folks out there can help you. Oh, it is. Excellent. Thanks. I'm going to be absolutely, can't do that, can I? I'm going to be merciless about keeping the speakers on schedule because, as I said, there's no slack. If by some miracle we get ahead, we'll save it, and maybe we will take a break in the middle of the session. Final note of this, of course, is the Khronos event. It's off-site because Khronos can't afford GDC rates. But there are many of our members who are talking about Vulkan at the show. These 3 are up tomorrow. I didn't put the ones we've already missed. I particularly recommend the practical development for Vulkan. At that talk, Dean Sekulik will speak as part of the talk about the Talos Principal Port. That was originally going to be part of our presentation, but we didn't want to duplicate, and he was going to do it there as well. Okay, so without further ado, a little bit of big picture stuff. The origin story starts actually further ago than we've talked about in the past. The OpenGL and OpenGLES working groups knew back as early as around 2010 that OpenGL kind of needed some architecture work, that it had gotten a little archaic and was having some issues because of it. We started a project back then, a joint committee to do re-architecture. And we did some brainstorming, we did some design work and requirements analysis, but it wasn't really a top priority for us, and it really didn't go anywhere. It just sort of dragged on. That all changed in 2014. The X12 was coming, Mantle was coming, Metal appeared, and we realized, hey, we have to do this now or we're going to be left behind. So we rebooted the project under a new name, GL Next, and began working. 2 things really made it work. One was all the key ISVs who had participated in advising the design of these other modern APIs said, we want an open version of this. And they all piled in and helped us make that happen. That was absolutely critical to our success. Another thing was that AMD, after some thinking about it, donated Mantle to us as a starting point, which was awesome, got us off to a flying start. There followed more hard work than I ever want to do again in my life. And at GDC last year, we decided that calling it OpenGL would not be true to the spirit of it. It really is a new thing. So the project was renamed Vulkan and disclosed there and launched exactly 1 month ago. It's the 16th today. 16th of February was our public launch date. This is where we started in terms of what we were trying to achieve. We had a vision. First of all, start from scratch, wipe the slate clean, architect it from first principles, and then a bunch of technical goals motivated by things we knew were wrong with the existing APIs in the open space. I'm not going to go through them in detail because you all know what they are. You all lived through that. What I will claim, without trying to prove it here, is that we kind of think we did this. Every one of those, I think I'm prepared to defend that we met that technical goal in some sense. I will admit that you can quibble about some of them. Clean. We said a clean modern architecture. Have you read the Vulkan spec? Well, you can argue about whether it's clean. If you think clean means simple, it's not simple. But there are good reasons for it. If you think about it, Vulkan, don't think of Vulkan as a graphics API. It's an API for controlling graphics and compute hardware. And so, of course, it has pixels in it. It has vertices in it. But it also has command buffers and descriptors and memory pools and all the things that real hardware needs to work. And that's where the complexity comes from. We did work quite hard. We made several passes trying to make it as regular as we could, to make the API signatures consistent, the arguments in consistent order. We probably didn't do it perfectly, but we did work hard and think about it. The other thing at the very end, the last goal was improved reliability and improved consistency. Everybody complains about GL bugs, and they complain about differences between implementations. I have to tell you the truth. It's early days. We have a bunch of implementations out there, but there's no content, or very little, to validate against them. We have a conformance test, but it's immature. We're investing very heavily in it, both the members and Khronos as an organization. And it will get better, but you do have to expect some issues early on. The other thing I would say is that remember that with Vulkan, as opposed to OpenGL, we only guarantee consistent behavior, or we try to, if your application follows the rules of the API. If you break any of the validity constraints on how you're supposed to use things, you get undefined behavior, because we don't want to impose the cost of checking for those errors on applications that aren't making errors. We have separate tools. We have validation layers on top of Vulkan that will help you find those errors in development. But the runtime is just straight ahead as fast as we can go. So don't expect us to work on delivering compatible undefined behavior if you do something undefined. Where we are today, I keep doing that. We launched, as I said, exactly a month ago. Not just the spec. We didn't just park a PDF out there. We did, well, there's the API spec, the language spec, SPIR-V. Data format is how we describe pixel formats, et cetera. And some important standard extensions, like for Windows system integration. Also man pages, though there are some 404s in there. Sorry. We're working on that. Software. There's a compiler that compiles GLSL, a version of it, to SPIR-V. There's a basic SDK, which Khronos really intends for you to take and build on and improve for your own purposes. There are third parties who are doing that as well, and we'll make those available, as you'll hear later. And a conformance test. And something we've never done before, it's all on GitHub in open source. This is motivated by our sense that, in addition to the goals I talked about before, as we worked on this, it seemed to us that we needed to change the way we related to the community to be more community-facing, more responsive to developer needs. We're a service organization. And so this is a step in that direction, is to put everything out there and let people have at it. In terms of industry support at launch, these 4 companies, Imagination, Intel, NVIDIA, Qualcomm, had conformant drivers the day of launch. Since then, 3 others have joined the club. There are third-party tools. As I said, a sort of bundling and improved SDK from LunarG. Karen and her team will be talking about that later as part of the deep dive. And there are also tools available from some of the IHVs. There was even a game, which is cool. We didn't know this was coming until like a week before launch, when Dean called us up and said, hey, I got this thing. Do you want to brag about it? So that's awesome. Thank you, Dean. Platform support. We are, cross-platform is in our DNA as Khronos and as OpenGL people from way back. It's what we want to do. We don't control all platforms. Windows, Microsoft's probably not going to go out of their way to expose Vulkan, but they're going to allow us to, and the IHVs are doing that. They're delivering drivers on Vulkan. As well, many flavors of Linux and special purpose platforms like Steam. And of course, as a mobile guy myself, I'm extremely excited that Android has announced that they're going to adopt this. Am I right about that there is now a public commitment for a particular version? Android N will expose Vulkan, which is so cool. And by the way, I should say, Google's commitment to the process all along has been awesome. They're spearheading the conformance test. They're investing very heavily, and it's fantastic. I wanted to say a bit more about the open source move. This was a new thing for Khronos. We've never really done anything like this before. We tend to sit in a little room and do our thing. And there are some reasons for that. New spec development, because of these things called patents, kind of has to be done quietly. But open sourcing all the artifacts related to 1.0 seems to have worked pretty well. We are still working on the CLA. We underestimated the lawyer throughput. So we can't take your pull requests today. That's coming, and it's coming as soon as we can make it happen. Probably within 2 weeks. Next week. Yay, thank you, Neil. Neil's leading the charge on that. So we'll start taking pull requests against both the code and the specification at that time. We take issues now. You can go to GitHub and file anything you like. The thing that has blown me away, we didn't really know what to expect. Would anybody notice that this was out there? We've had incredible response. I mostly track the spec because I'm a spec guy. We've had since launch 127. Well, this was Sunday night, 127 issues opened, which is awesome. Some of them are, you dummy, why did you do it that way? Well, you might be right, but we can't do anything about that. The spec is out. But we've had lots of people pointing out, the header would be easier to use if you changed the defines and guards to work this way. So we did that. People have pointed out errors. You used it's a num when you meant that one. We fixed that. It has really been great for us, and it has helped us to rub the rough edges that every new spec has off in record time. I will say, if you read the fine print there, 66 issues open, 57 closed on Sunday night. We're doing our best to be responsive, and we have dedicated time every week to bash through publicly raised issues as fast as we can. We're behind right now. We are working on our process to catch up, but we are committed to making it happen. This is a long-term, and as I said, we'll make it happen. So to close up my portion of the talk, and Jeff's getting ready back there, turning back to the theme of where did this come from and how did we get here. From a business point of view, from an ecosystem point of view, these are the industry segments and the industry players that made Vulkan happen. And of course, I'm incredibly grateful to them for that. They paid the bills. From my point of view as a committee chair, of course, I know companies don't do work. It's people who do work. And so from my point of view, these are the people who made it happen. This is the whole Vulkan team and the whole SpearV team, except for a few guys who didn't come to the meeting and did the whole thing on the phone. How you do 3 days of meeting on the phone, I don't know. But I'm eternally grateful to them for their hard work and for making this happen. Many of them, the people you're going to hear from today, are in this picture. Just a few are not. Our next speaker, you could start on your way up here. The spec was crowdsourced, kind of. It was a community effort. But if there's one guy who was indispensable to the project, and who certainly by commit hash count was the most active contributor to the specification, it was Jeff Boltz at NVIDIA. He's going to talk about philosophy of Vulkan.
Thank you, Tom. So my name's Jeff Bowles. I'm a software engineer at NVIDIA. I've been working on Vulkan and previously OpenGL for more than 10 years. Today I'm going to talk about some of our design goals for Vulkan, including what it means to be an explicit API, some portability issues, and how our goals translated into the final API, giving some examples with multithreading and render passes. So what does it mean to be an explicit API? It's really about providing information at the right time. And the right time is usually early and off the clock. This means creating pipelines, allocating memory, all the expensive stuff is under the application's control. And it also means no driver magic on the clock. Less driver guessing, less late decision making, less heuristics. And so that translates into simpler drivers, but it also gives the application better scheduling control over where CPU work happens and where GPU work happens. And we do this not really by making a low-level API or a thin API. We do it by maintaining higher-level abstractions. And this is in contrast to a truly low-level API, which to me means a thin layer over a specific hardware implementation with little abstraction. And that really wouldn't be possible given the wide variety of hardware that Khronos supports. If we had a truly low-level API, applications would be forced to code IHV-specific code paths, and that's not something we wanted. That was an anti-goal for us. So Vulkan tries to be thin for the work that happens on the clock primarily. And there have been some catchphrases in the last few years, making such and such the app's problem and getting the driver out of the way, and those aren't really problem-solving. That's not really what we did with Vulkan, at least in my opinion. And so, in a sense, we solved a different problem than we set out to or than we were asked to. But I think we solved the right problem, and I think we're better for it. So portability is obviously hugely important in Khronos. It should be possible to write a Vulkan application that can run on a wide variety of hardware, and moreover, it should be possible to write a single code path that can run efficiently on all that hardware. So it's really important to avoid mutually exclusive code paths. And a couple examples of where that came up. Some hardware has fixed function blending and fixed function vertex fetch, and others just use programmability to implement it. So to avoid that kind of dichotomy, we keep the fixed function description in the API. It's part of the pipeline creation state, and it can be translated either to fixed function hardware or to programmability. And that all happens during pipeline creation. All the information the implementations need is there. There's no draw time recompiles to deal with it. So there's really a strong desire to avoid forking the ecosystem due to those sorts of implementation details. In general, we want to limit the differences to the kind of things that can be expressed as caps bits or limits. And Vulkan does have caps bit hell right now. But we're trying to organize that into feature levels, and that's something we should have available soon to give people a real target to code to. Here are some examples of state that is ignored on some implementations or things that just behave differently if you venture into undefined territory. Image layouts are mostly ignored. Layouts and layout transitions are mostly ignored on NVIDIA's hardware, but they're used on AMD's hardware and on some other implementations. So if you were coding on NVIDIA and you had a bug in how you deal with image layouts, you might not realize it, but then if you ran somewhere else, you could have lots of corruption. Similarly, there's this buffer image granularity parameter to memory allocation, and I think that only applies to older NVIDIA hardware and not to anybody else. So if you happen to violate that, then you would have massive corruption. There are other differences like command buffer state is naturally inherited or leaked between command buffers on some renderers, but not on others. There's some Tyler-specific state that would not apply to immediate renderers. So these are all things you need to watch out for, and they're examples of the kind of undefined behavior that varies from implementation to implementation. So it's really important to validate your application using the validation layers. That's the tool we've built to try to defend against this. So it's not good enough to just test your application on your own system, see that it renders correctly, and call it good enough, because it's not good enough. One limitation of the validation layers right now is that they only validate against the limits and caps bits exposed on your hardware. But there's a project called VK-JSON that defines a file format and tools to import and export caps bits and limits. And that's going to get eventually hooked up to the validation layers. And then you'll be able to validate as if you were running on a different implementation or running against a specific feature level or whatever. And so I encourage people to use the validation layers and to contribute to them. So multithreading was obviously a disaster in OpenGL. And so it was a top priority for Vulkan to get right. So here's a quick summary of how multithreading works in Vulkan. All objects are not threadifying, and this means they can be used on any thread. There's no thread local storage. There's no COM-style apartments. You can use them anywhere. However, most Vulkan objects are not thread safe, and this means the driver does not do locking and mutexing for you. Instead, each use of an object is classified as being externally synchronized or not. And an extern sync usage allows no other concurrent use of the object, and that usually means the object is being written to or modified. So some examples of that would be destroying any object is extern sync for that object. Recording commands into a command buffer is extern sync for the command buffer. Submitting command buffers to a queue is extern sync for the queue. And then non-extern sync non-extern sync uses are allowed concurrently for the same object, and that's usually read-only accesses. So 99% of the time, when something is non-extern sync, it means there's no synchronization necessary, and only very rarely does it actually mean that we designed it to be internally synchronized, and the driver will necessarily do some locking. And that 1% is for pipeline caches, and I'll touch on that in a few slides. Additionally, we added some new objects to the API, primarily to assist with multithreading. If you think about how command buffers allocate memory, it's all automatically managed by the driver, or almost all automatically managed by the driver. As you're recording commands, the system automatically allocates chunks of memory to record them into, and there's a trade-off to make. If you allocate small chunks of memory, then you have to go to the allocator frequently, and there could be a lot of locking contention. On the other hand, if you allocate large chunks of memory, then you can end up wasting it. So descriptor sets have a similar problem. It's potentially even worse because the descriptor set allocations have a fixed size. And so we introduced these pool objects to assist with scaling here. So from the driver's point of view, these pool objects are intended to be implemented as simple lock-free allocators. And they're extern sync everywhere they're used, so the driver doesn't have to do any locking. And from the app's point of view, the intent is that you would use a unique pool per thread. Or more realistically, you would actually use multiple pools per thread, round-robining between them, between frames. That means that the driver doesn't have to do the locking because it's extern sync. The application doesn't have to do locking because it's only using one in each thread. And so this is an example of the driver and API and application all cooperating to solve this problem, rather than just making it the application's problem. The next object I wanted to talk about is pipeline cache. A pipeline cache is an object that captures reusable information during pipeline creation. It's similar to ARB-GET program binary. It's also kind of similar to the D3D12 cached blobs. The D3D12 cache blobs have an issue that was pointed out to us during Vulkan development by one of our ISV members, and that's that they're too unique. You get a distinct blob for every pipeline you create, and so even if there's only one tiny little different bit of state in the pipelines, in two pipelines, you can't actually share the blob between them. So we ended up with a design that's actually more similar to what some drivers have already implemented, which is automatic disk caching of shader compiles. But the automatic disk caching has the first run problem. The first time you run an application, you haven't seen the shaders before, they're not in the cache, and you stutter each time shaders get compiled. So pipeline caches attempt to address that by not only offering reuse within a run, but also being able to save it out, reuse it on a second run, or even share it on another system. So what I would like to see in the long run is systems like Steam or Battle.net actually distributing these as part of application installs for whatever the newest drivers are. And so then you could have a great experience not having the stutters on the first run. So some examples of how pipeline caches can reuse things. So for example, if an implementation supports separately compiling shaders, like vertex and fragment shaders, then if you have one you've already compiled and then you mix and match it with a different shader, that could hit in the cache. Alternately, if you have the same combination of shaders with just different pipeline state, and that pipeline state doesn't affect the shader compile, then that could also hit in the cache. Or if you have the same shaders with different specialization constants, that could hit. And really, it's just whatever happens to work for an implementation. There's a lot of freedom for the drivers to optimize this, doing whatever is best for their system. And one of the reasons I wanted to mention pipeline caches is that they have this unique threading interaction. They're, I think, the only instance of an object that's internally synchronized by design. And the reason for this is they're used in the create pipelines commands. And these are the most expensive commands in the API. They can take many milliseconds. And you can't expect the application, we as the API designers can't say, you have to take a lock around that command. It just wouldn't be good design. So instead, we leave it to the driver, and the driver is able to take a lock at a much finer granularity. It can do it only when it's actually probing and adding data to the cache, and it doesn't have to do it. It doesn't have to hold on to it while it's doing shader compiles. And so this allows a single cache to be used and shared between multiple threads. So render passes are maybe the most interesting new feature in Vulkan. The original goals for render passes was to separate the blit commands and memory updates from rendering commands. And this is really critical on tilers because doing a memory update in OpenGL would require flushing the tiler. And that obviously dumps the frame out to memory and has to read it back, and that's really expensive. But it's also a cost on immediate renderers. Doing a blit on an immediate renderer usually requires draining all the previous work, doing the copy, starting up the following work, and there's a lot of dead time that happens there. Waiting for threads to finish, waiting for memory latencies for the copy, waiting for the system to fill back up again. It's not an efficient use of resources. So separating out blits from the real drawing commands is valuable everywhere. And render passes also originally had some of this tiler information about loading and storing frame buffer attachments and doing multi-sample resolves. But render passes evolved into something more interesting, which we call multipass. So a render pass can support multiple subpasses, where each subpass can use different frame buffer attachments or can share frame buffer attachments with the other subpasses. And so the render pass describes a graph of the subpasses, and each node in the graph is a subpass description, and it includes a list of which render target attachments it uses and their formats. Each edge in the graph is a dependency and describes how the destination subpass depends on the source subpass. And each edge also indicates whether the dependency is tileable. So you create your render pass up front, and then when you record a render pass instance into the command buffer, you record the commands for the subpasses in order, calling next subpass in between. And then when you execute that command buffer, the subpasses execute according to the graph described in the render pass. So if a dependency between two passes is not by region, that means it's not tileable, then a tiler will iterate over the tiles in the first subpass, complete all of those, and then iterate over the tiles in the second subpass. If the dependency is tiler friendly, then the tiler can flip the order of the loops, switch the inner and outer loop, and it can iterate over the two subpasses for tile 0, and then the two subpasses for the next tile, and so on. And by doing that, the data from subpass 0 is still available on chip and can be read when executing the second subpass, and that can avoid having to dump it out to memory and read it back. So this is a really big efficiency increase, especially for tilers. And the multipass or the render pass object is compiled before it's used, And this gives an opportunity to allocate any kind of finite resources. For example, allocating the render target data into the tile memory. So this figure shows an example where there's these 3 subpasses, there's 6 attachments, and attachment number 2 needs to be spilled out to memory after the first subpass and then restored for subpass 2. And the pipelines are compiled against the render pass they're going to use, or actually technically against a compatible render pass. And so when you do the pipeline compile, it knows where to access all the resources, and it doesn't have to do any state-based recompilation later on. So for people who are curious, I'd encourage reading the Pixel Local Storage extension. This was, I think, an ARM extension. Imagination. Oh, sorry, Imagination extension. Okay. And it's kind of the lower level version of this functionality. Using it required modifications to the fragment shader, and it only worked on certain hardware, and so it wasn't as widely applicable. And what we have with multipass render passes, it can run, you can write your application in a way that you can take advantage of this performance feature, but you do it in a way that you can run your code on any system. You don't have to rewrite your shaders for it. And despite that, it actually offers potentially better performance than the lower level extension. So this is an example of when building a really good abstraction for this actually benefits everybody, even the people who had previously done the lower level extension. So to conclude, early on we were really concerned, as Tom mentioned, about Vulkan only addressing a really small section of the market, only really being viable for those companies that had a lot of resources and could really deal with different code paths for different situations. But as things developed, we actually found ourselves maintaining and even adding new abstractions to the system. And despite that, they didn't come as a performance cost. I think they actually benefit everybody. And so I think that means we found a really good design point. And I think Vulkan benefits from having these abstractions and not really from being a truly low-level API. So that's my last slide. I'd be happy to answer any questions people have. Okay.
Come on, guys.
I raced through it to leave time for questions. All right.
We know that Mantle influenced the design. How much did Apple's Metal influence the design?
Okay. I think the question was, Mantle certainly influenced the design. How much did Metal influence the design? Metal gave us a big kick in the butt, right? In terms of getting started and really committing to the project. In terms of technical, not sure how to describe it, but I think it was more in terms of getting us moving that we benefited from the Metal announcement, and not so much from technical features in it. Yes?
How do you feel about the balance between the two? Metal has less details, less edges, less stuff to worry about.
Yeah, so the question was, I'll paraphrase. There's a design trade-off between Metal and Vulkan. Metal is a little more challenging to use, Vulkan is a little more challenging to use. Metal is a simpler API, easier to port to. I think there's a place for both, and it's similar to asking the question of where does OpenGLES and OpenGL still live in the ecosystem. And I think there's a presentation about that later. But I think depending on people's developers' experience levels and what they're comfortable with and what systems they want to target, I think there's a good place for all the different APIs. Yes?
About the pixel local storage, is going to be any way to know the amount of storage that you can count on? Because if not, even if you do the code agnostically, if you put too much data to be stored there, you can go out and then you are going to run into performance problems. Is there any way to control that?
Okay, so the question was, using the pixel local storage model as an example, how do you know if you're going to run out of memory, and how can you tune to avoid running out of memory? That information is not exposed in the API right now. That might be a good situation for a vendor extension to expose a hint for how much to use. But one of the benefits of the API as it is now is that you describe how you're going to use things, and then the driver can decide which things are best to spill based on whatever the hardware details are. So if you go over the amount of tile memory available, it doesn't just fail. The driver will spill it intelligently and hopefully do a really good job of it. Hopefully better than an application could have done with the lower level API. OK, well, if there's nobody else, I'll turn it over to Graham.
Okay, hi everybody. I'm Graham Sellers. I work for AMD on Vulkan stuff. And this is the first session in our deep dive sort of block of the day. So I'm going to get into some API details and best practices for using part of the API. In particular, I'm going to be talking about memory allocation in Vulkan. It's something that's kind of easy to get wrong, but it's also a tool to really make the most of the sometimes limited resources that are available to your application. So start with the memory management topics. There's denial, there's anger, there's bargaining, and so on. I mean, don't get me wrong, it can be really painful. But if you do it right, it's very, very powerful. So actually what I want to talk about, there's three things. First is pooled objects. Jeff just touched on that in the design overview. I'll give some concrete examples here. There's host memory allocation, which is system memory, malloc, basically. And then there's device memory allocation, which is the memory that is used to back buffers and textures and images and things that the GPU will be using. Okay. So first of all, pooled objects, right? Some of the objects in Vulkan are allocated in pools, right? These are command buffers and descriptors, which Jeff just mentioned. Also, queries are managed in pools as well. They each have a object type associated with them. You can create them and say how many of the objects you want, or other heuristics about the pools, right? The pooled objects are not thread-safe. So you create several pools, you'd assign a pool, or maybe more than one pool, to each thread, and then that thread is then free to go and allocate from the pool objects that it needs on the fly without worrying about contention with other threads. It's lockless. It's basically a single-threaded model once you have the pool. And it's up to the application that no two threads hit the same pool at the same time. And also, when you free the pool, all the objects in it are returned to the pool or freed. It's also possible in some cases to reset the pool and say, right, put everything that I've taken from the pool, put it back. I'm going to start again. So this is kind of like a frame per frame thing where you'd be allocating objects on the fly from the pool, and then when you're done with a chunk of rendering or with the frame, you return them back to the pool, and it all goes real fast. Okay. So the command pools are where command buffers come from, and the reason for this is that as you call Vulkan commands, there's no practical upper limit to a command buffer. It would have been very difficult to say, I want a command buffer that's going to hold 400 commands, because the size of a command is completely hardware dependent. So we needed to be able to allocate these things on the fly. And so that memory comes in the pool. And the application guarantees that you're never going to be building two different command buffers allocated from the same pool from different threads at the same time, because building the command buffers sort of indirectly accesses that pool. But a single thread can still create multiple command buffers on the fly. Add a command to this one, add a command to that one, and so on. And they can come from the same pool. But the thread owns the pool, right? So it's a high-performance, single-threaded allocator. The next type of object is the descriptor pool. This is where descriptor sets come from. And the reason for this is, well, we probably want to be able to update descriptors on the fly, page in textures and bind them into pipelines. into command buffers so that you can use them from your pipelines. But the descriptors themselves, at the hardware level, are generally kind of big arrays of homogeneous stuff. So if you want 1,000 textures, it doesn't make sense to manage them as 1,000 separate little tiny memory allocations. You want just a big fat array of 1,000 things. And then when you want some for a descriptor set, you just pull them from this pool. Again, the pool is not thread safe. You can either, say, use a dedicated resource management thread that owns the pool, or you can create a descriptor pool for each thread, or however you want to manage these things. Right? Take a lock around it. It doesn't matter. I mean, don't do that. But yeah, I mean, it's your problem, application's problem, or opportunity, I suppose. And then query pools, they work slightly differently than the other pool objects, but they're conceptually the same. You have this sort of large number of homogeneous objects, right? A query object, in many cases, might just be a 64-bit number in memory somewhere. So making a separate allocation to create a query object would not be a good idea. It wouldn't be performant. It would fragment your memory, and it would make it very hard to batch up queries. And a lot of applications render 300 things with a query around each one, and then say, give me all the results from all the query objects. If they were all over the place in memory, that would be a terrible thing to do. So query objects are allocated in pools. And it's a contiguous allocation, and a query itself is just an index within a pool. Right? So that makes batching results. Give me all the results from these queries in this pool, and then grab the results. Okay, so those are the sort of three pool objects. This isn't really directly related to memory allocation as much as object allocation, but it is kind of an important topic. Okay, but now we get on to the actual memory allocation. Right? We've got host memory, we've got device memory. Host memory is the CPU memory, the stuff that you get a pointer to and just poke at. Comes from malloc or new or whatever you have. And device memory is the device, the memory that's physically part of the GPU usually, or is at least memory that the GPU can see and use. So first we'll talk about host memory. Right? Host memory can be owned by the application. You don't have to use this feature. The driver can call malloc or whatever it's going to do internally, but it does allow you to provide your own callback functions to allocate memory. So most object allocation functions take a pointer to this VK allocation callback structure, which contains a user data pointer, which can be anything you want, and then a list of allocation functions. There's a hierarchy of these memory allocators. So when you create your instance, you hand an allocator, and the instance can allocate memory it needs from that allocator. When you create the device, you're giving it an instance against which to allocate the device, but you're also giving it another allocator. It could be a different one. And the device could allocate some memory from the instance, or it could allocate memory from this device level allocator, and so on down the chain. And as you create objects, depending on how the driver wants to manage the object, it may use the per object allocator, or it might walk up the chain. I can get into the technical reasons why you might want to walk up a chain of allocators. And you don't have to supply every single one of them all the way down the chain. You could just say, right, for everything in this instance, use my allocator. Right? But the granularity is there that you can use a per object allocator if you wanted to. So the allocation callbacks basically have function pointer types. You get a alloc, a realloc, and a free function. They look like the prototype I have on the screen here. Free and whatnot are this similar. And so you have the user data parameter is the one that came from that allocation structure, allocator structure. You get a size, an alignment, and then a scope in the allocator, and the scope tells the allocator what kind of thing you're making, right? So you might even batch up your allocator so that small allocations come from here and big allocations come from here. Short-lived allocations come from this chunk of memory, and long-lived allocations come from that. And so you have a lot of information. It's not just new unsigned char, right? It's an actual allocator kind of structure. And of course, you can shove whatever you want in user data. So usually it would be a pointer to an instance if you're a memory allocator class or something like that. But it can be anything you want. When the driver calls these functions, it's called from the thread that produced the need for the allocation. So if you call vk command do some stuff, and that requires the driver allocates some memory. That thread will be the one that calls you back, right? So your allocator doesn't have to be thread safe if you can guarantee that you're only ever going to get called back from one thread. But what might happen is that even if you're using a per object allocator, that if the driver walks up the hierarchy, that you've got two threads creating objects or whatnot, and in both threads, the driver decided to walk up to the devices allocator, and now you could be calling the devices allocator from two different threads. So what you might want to do is make a thread-safe allocator for your instance allocator, device allocator, and then use a fast, free threading allocator for your per object allocator. And then when the driver does use the per object allocator, it goes fast because you can guarantee that you have a per thread allocator, for example. There's also going to be some cases where there are internal memory allocators that for whatever reason the driver can't use your allocator. Some examples might be you might need a special allocation for executable code if your driver is jitting something. It might need some special alignment or caching properties that can't be readily expressed by the callback function. But even in those cases, the driver can tell you that it's doing those things. So that we have the internal allocation and internal free functions. And these have the same parameters as the alloc and free functions that are normally used for allocating memory, but you don't have to actually, they don't return anything. They're just informational. So they're not going to make your application run any better by hooking these things up. You can hook them up in debug builds. They're there for tools and profilers to hook up memory allocations. So even if you don't use the memory allocators, you could hook up the internal notifications so that when the driver makes its own allocations, you can at least kind of see what it's doing. Finally, when you want to free host memory, the destroy functions also take an allocator, which is a little bit counterintuitive, but it's actually taking the per object allocator and then stuffing that state inside the object, in many cases, would make the object measurably bigger. So if you've used a per object allocator, it's your responsibility to pass something back that is compatible with the allocator you used to create that object. So by compatible with, I mean you don't have to physically pass the same allocator structure pointer into the API. You just need to make sure that whatever is in that structure, the callback functions will free correctly, the user data parameter will be interpreted correctly by those functions, and so on. I said that we don't always use the allocator. For one particular example is, well, if you pass me a per object allocator to allocate some dinky little object, making thousands of little tiny memory allocations might not be a good idea. So I might implement my own pool allocator. Well, now I can't use your per object allocator because there isn't a per object allocator. Thousands of objects might have come from the same allocation. So which allocator do I use to make that allocation? That is a case where I might walk up the hierarchy and use the device allocator to allocate memory. There's other cases where we internally have constructed an object and attached it to something else. We might reference count it, or we might otherwise keep a reference to it. And so we might not free it immediately. When you call free, we might put it on some kind of list of things to get freed next time enough stuff has been freed, and so on. Then call your allocator a bunch of times in a row. So these are all things to watch out for. Don't expect that just because you passed us an allocator, it's going to get called every time you create an object or anything like that. But the mechanism is very powerful, and it does allow you to at least see what we're doing, if not control what we're doing. OK, and so now we move on to device memory, which is possibly the hairiest part of the API, the thing that's easiest to do, the most naive job of, but also a very powerful mechanism for managing GPU memory, and kind of thing that console people have been asking for years, and finally you can kind of do a lot of this stuff. So most resources on the GPU require some GPU memory, and this is memory that is usually physically attached to the GPU. Might be special dedicated memory, but it's memory that's at least accessible to the GPU. And in Vulkan, the resource, which is an image or a buffer or a texture, is a separate object from the memory allocation. Okay? And one memory allocation can host or hold many resources. And you can even put them on top of each other and do crazy stuff with them. We allocate in free memory with VK allocate memory and free memory, and then we attach the resulting objects to the resources with bindImageMemory and bindBufferMemory. Images and buffers are not the only types of resources that require GPU memory. In many cases, something like a query pool might require GPU memory, or PSO might require some memory. Obviously, command buffers require memory. But in those cases, we manage that directly inside the driver. Early versions of the API had every object needed memory bound to it, and it became very onerous very quickly. So we got rid of that. So it's really just buffers and images that require application managed memory. So memory is allocated from heaps, but within a heap there can be multiple types of memory. So you have this array of memory heaps and an array of memory types. And the memory types have an index back into this array of heaps. Right? So the heap properties are things like the size of the heap and whether it's local to the device. Right? The type of the memory indicates caching properties and coherency properties, and you might even have more than one type of memory that outwardly look very similar, but different resources might require different types of memory. You can query the number of heaps and the number of types using the VK get physical device memory properties API, and this will give you the arrays of both the heaps and the types. What's important to note is that when you allocate a type of memory, it comes from the heap that it's a part of, right? So the first thing you do after you've created the resource, you always create the resource first, is you get the memory requirements for that resource. I'm going to talk about images here, but the APIs for buffers are quite similar. So you call this getImageMemoryRequirements API. You pass it an image, and it hands back data in one of these memory requirements structures. And what you get back is a size, an alignment, and a set of flags that say what the properties of the memory that it's going to need are. You can pick the memory type from the array of types that the device supports by just matching the bits in this memory type bits against the types that the driver has supported. And there's some sample code on the website that says what the appropriate mechanism for iterating through the types is to match them up with what the image says it needs. So we call allocate memory. We pass the allocate info, and this just gives you the size of the allocation and the type. And this is the index into that array. When you allocate the memory comes from the heap that the type refers to. So I might allocate a megabyte of one type of memory, a megabyte of a different type of memory, and now I've allocated 2 megabytes from the heap that they might both be a part of. So there is this separation of types. The image, the memory to the image by calling bindImageMemory. There's also a bindBufferMemory, and the image consumes as much memory as it needs, starting at memory offset within the memory object that you've given. And you can and should create large memory allocations and then just place your resources in them. You can even place them on top of each other. But in that case, you have to manage the hazards. Make sure that 2 pieces of memory or 2 images that use the same piece of memory aren't both in use at the same time. It's also not well defined at all, really. If you place 2 images on top of each other in memory, that writing to one and then reading from the other will give you anything useful. So you can do that, but don't do that. Like most things in Vulkan, you can do it, but don't do it. Okay. So finally, we get to freeing device memory. Just call VK free memory. And again, it's your responsibility to resolve hazards. There's no garbage collector or anything. You say free, the driver will free, or it could right there on the spot. So if you have work that's in flight on the GPU that's a few milliseconds out from executing, then in a few milliseconds you'll crash because you just freed the memory that it was about to use. We do make a guarantee that we're not going to like hose the entire system. We have kind of various security things in there that stop us from trashing other processors, but your application will definitely suffer the consequence of getting this wrong. So again, be careful with that. It might mean that you need to stall the GPU in order to free memory, right? At very least, you're going to need to use a fence and then track which fence corresponds to which allocations, and then wait for the fence, and then free it. So what you might actually consider doing is simply reusing memory objects. When you want to free something, just keep the memory object, unless your application is terminating, in which case just idle the device and free all the memory. That's probably the best strategy, I think. So, some tips. Be smart, not silly. So, the user object pools, obviously the API says you have to, but be smart about it. Don't just like create thousands of pools and then use 2 objects out of each one. Make your pools nice and big, and then use them wisely. Don't just mutex around them, create a pool per thread, and so on. If you have to implement a mutex, don't just take some giant global critical section. I mean, this is a multi-threaded API so that you guys can use threading. So be smart about that. And remember that when you free the pool, you free all the objects in it. So the same applies to freeing device memory. If you free a pool while there's some queries in flight, the queries will probably trash something and your app will go down. So don't do that. Manage your own system memory if you want to. We've been doing memory allocation in drivers for years, and while we get the odd complaint here and there, we're fairly good at it. So only do it if you think you can do a better job than the driver. And be aware that a driver might ignore you and not use your allocator the way that you think it might. If you do write your own system memory allocator, the easiest thing to screw up is just wrapping malloc and then returning whatever it returns. That's the silly side of things. Don't do that. We can definitely do better than that in the driver, but you do need to make sure that you support alignment properly. Every object reports an alignment requirement when it asks for memory, and this actually can make the difference between runs and crashes. Because if we've asked for memory of a particular alignment and then we go and start using SSE unaligned loads and stores on the memory, this happens. You like my demo? There. Okay, we'll go on this side. Yeah. And also, there's nothing for you to see inside the allocations. When we ask you to allocate memory, don't keep the pointer and start getting smart and trying to poke in there. There's no reverse engineering. There's no secret sauce or anything like that. So yes, you have pointers to internal driver structures now, but they're not useful for anything, so don't use them. And then finally, on the managing GPU memory side, you do need to write your own memory allocator. The driver doesn't do this. This is not optional, right? Every image, every buffer needs memory allocated to it. The first sort of slew of applications that we saw just went, create texture, how much memory do you need, allocate memory, bind them together, submit. And then we saw these submissions coming through with 3,000 memory allocations. It was really disastrous. You're going to need to write a memory allocator. I'm 100% confident that 30 seconds on Google will find you 7 that you could use. Any of them are probably reasonable. But it doesn't have to be crazy smart, but just don't be crazy stupid with it either. Try to pool your allocations together. Try to get lots of objects into each allocation. And try to make sure you, again, obey all of the alignment restrictions. What you might see is that tiling corruption happens sometimes, right? And I think that's about it, I will say. Thank you. If there's any questions about memory allocation, I don't know if I have time, but.
No, I'm going to talk into your mic.
Right,
so what's happening here is we're going to power cycle both projectors and hope they both come back while he's taking questions. And that way we don't get behind. So.
All right. Questions? We have a question at the back.
This is slightly tangential to what you presented, but it has to do with allocation. Do you have any general strategies for dealing with the different types of memory parency if you're working on a system that may or may not support device local or host visible with parency?
The general strategy, the question was, do I have any advice for dealing with coherency or other memory properties when you don't know what kind of device potentially that your app's going to run on and so on? And my general advice is don't ask for something unless you need it, right? So if you don't need something to be coherent, don't ask for coherent allocation. If you don't need something to be mappable, don't ask for it to be mappable, right? Because on a UMA, everything might be mappable anyway, so then you go and ask for everything to be mappable, and it just works. And then on a system that's not a UMA and it's got a little tiny slidey window of mappable memory and you've asked for mappable memory, you run out of memory instantly. Even though there's like 4 gigs of memory on the graphics card, you can't map it all. So yeah, for coherent and for persistent maps and for mappable at all, only ask for it if you really need it. Right? Treat it as a scarce resource. Because it's working now. Any other questions? No? Okay, excellent.
I want to talk a little bit more. Thank both our speakers for being awesome about staying ahead of schedule. So what that means is we're going to continue for maybe one more talk, and then I think we do have time for a break. Hang on to your seat, put your backpack on it or something. But if you want to, we'll resync maybe after this next talk.
So good afternoon. Hope you're all doing well. It's a beautiful day outside. Thank you so much for coming in here and spending some good geek time in San Francisco. It's one of the things that I love about this town. Both it's gorgeous outside and it's really interesting inside. I'm Bill Isaiah Kane. I work for Qualcomm, and I'm one of the volunteers at the Khronos group working on the Vulkan specification. Let's try that again. Sorry about that. Okay, so I'm talking about command buffers and render passes and subpasses today. Jeff went into some of the overview of them. I'm going to go in a little bit deeper and hit you with some of the bits and bytes and what's going on. And also, Graham talked about the command, the pools, and I'm going to go into that starting. So the command buffers, command pools and command buffers. I want to make sure that you understand that there are several states that command buffers go in, and that we have primary and secondary command buffers, but no more, just primary and secondary. So here's a diagram of the way the pools work. Pools are in the middle, and that's where allocation of the objects comes from. Host memory, Graham was talking about that with the allocators that you can provide. So either we'll use the device allocator or the instance allocator or your per object allocators, depending on how you've used the API. And like Graham was saying, we're going to use one of those allocators and you're not necessarily completely convinced which one we're going to get to you. So host memory gets pulled into the command buffer pools. The command buffers take that memory from the command buffer pools. When you reset a command buffer, it goes back into the command buffer pool. And when you reset the command buffer pool, the memory goes back into the host. All right? So that's the fundamental movement of memory through this whole pool to the command buffers and back. Command buffer pools, as we were all talking about, they're not thread safe. So you need a different command buffer pool for each one of the threads you might be using. Now, you can share a command buffer pool among multiple threads. Don't get me wrong. but you're playing a little bit with a hand grenade where you pulled the pin out of. If you carefully are handing that command buffer pool back and forth between threads and never simultaneously accessing that command buffer pool and never actually doing some other commands with the command buffer pools that are implicit, you can successfully hand those command buffers back and forth across the threads. But generally, probably the safer thing for you to do on your app, and probably the easier thing for you to do on the app, is think about creating a command buffer for the pools that need them. You're going to have creators and consumers of your objects. And in fact, you'll probably want to have multiple command buffer pools per thread, and I'll go into some of the reasons for that in a moment. While you're creating the command buffer, there's 2 bits that I want to go into. The command buffer create transient bit. And that's going to tell you that these command buffers are going to be relatively short-lived. How short? Well, it's a combination of how long they're going to be around and how many times you might be submitting it. Clearly, if you have a one-time instance command buffer where you're submitting it once, that is about as transient as you get, so long as you didn't create it and then wait 65 years to submit it. So if you create a command buffer, then submit it, and then turn around in a frame or 2 frames or 3 frames, recycle that command buffer, that's what we mean with a transient kind of a command buffer. And then the command pool create reset command buffer bit. Can I ask for volunteers to remember the name of that? Who wants to raise their hand and say, okay, you've got to remember VK command pool create reset command buffer bit. You'll only have to remember it for a short amount of time. We only got a few slides to go to where we reuse that bit. That's to say that when I create a command buffer, I can individually reset it. If I don't set that bit, the only way I can reset the command buffer is by resetting the pool. Okay? So, resetting the command buffer pool. I can reset the command buffer pool. That will reset all of the command buffers that are out there. I can optionally reset the command buffers back to my own pool. So I will hang on to that memory that the host had given me, and I can reuse that as the driver back out to future command buffers. Or I can reset the resources in the command pool at the same time, and that will move the memory out from the command buffer back over to host memory. I think I had them this way on the slides, didn't I? Sorry. So from the command buffers to the host memory. The states of a command buffer. When you first create a command buffer, it's in an initial state. When you are recording the command buffers, it's in the recording state. Fairly straightforward. After you get done recording the command buffers, it's in an executable state. And finally, it's in a pending execution state if you submitted them or you've executed them from a primary command buffer. This is where the allocation allocator stuff comes in that Graham was talking about. So you can allocate command buffers. Please allocate bunches of command buffers at once. Don't allocate them once at a time. That's the kind of thing. You're going to want to manage multiples of them at one time or another. And when you create the command buffer pool, that pool then you tell me I want to allocate primary command buffers or secondary command buffers out of that pool. And then whenever I create a command buffer out of that, it will forever be either a primary buffer or a secondary command buffer. And I can, of course, free the command buffers. So resetting. Who's my volunteer who remembered the bit? All right. If you set what bit?
VK command pool reset command buffer bit.
Very nice. If that command buffer has been created with that command buffer bit, then you can do a reset it. And now, again, similarly to the resource going back from the pool to the system, I can either reset the command buffer and say, you command buffer, still hold on to your memory, or you command buffer, bring that memory back to the pool. And that's somewhat useful in one way of thinking about it is if your command buffers are generally approximately the same size, letting the object hold on to its own memory is probably fine. If the object is one time very, very tiny, one time huge, and then another time really, really tiny, recycle that back to the pool so it can possibly be more efficiently used. However, all of that, different allocators are going to be using things differently in that way anyway. So recording. You can begin recording a command buffer And you have the command buffer begin if info. And there's a bunch of flags, again, these interesting little bits. The one-time submit bit is not a hint. You are telling us you're going to submit this once. And after you submit that, you're either going to recycle it or you're going to begin it again, depending on whether or not you can do it more than once. You can submit it more than once, because this is Vulkan. We're not going to keep you from submitting it more than once. But if you do submit it more than once, what you get is undefined. Okay? Render pass continue bit is for the secondary command buffers. And that's to allow you to basically pass in a little bit of state information into the secondary command buffer while you're building that. You might be building that in a completely different thread. And then that way you can have the seamless transition from primary command buffers to secondary command buffers for a limited amount of the state info. And finally, the simultaneous usage bit, which says that this command buffer might be used in multiple places in a single primary command buffer. So if I'm going to execute it multiple times or possibly in multiple different places. Again, set the bit and don't overset the bit. If you set the bit and violate the results, your validation is wrong, you get undefined results. If you forget to set the bit and you used it, if you set too many of the bits, then you're over telling us. So we want you to tell you the truth about what it is you're doing with all these objects. And so the things that you end up coming in with the inheritance info are the render pass object, the subpass info, the occlusion query enable, the query flags, and the pipeline statistics. The last three are kind of these special cases that allow you to have queries active while you're executing a secondary command buffer. And then, of course, you can end a command buffer. One thing that's key on all this, because I was talking about the different states of it and the object lifetimes. Command buffers have the initial state. You can always begin recording a command buffer in the initial state. Has the recording state. Can I begin a command buffer if I set that bit? I'm sorry, I won't make you say it again. But if you can't reset the command buffer individually, once I've begun the recording a command buffer, I can't reset it, I can't begin it again. If I haven't set that bit, I can change my mind in the middle of building during recording. Once I've ended the command buffer, it moves into the executable state. And once I've submitted or put it into an execution of another command buffer, it's in pending. I can't begin a command buffer on a command buffer that is in a pending execution state. And I can't also free it. I can't reset it. I can't do a number of things while it's in the pending state. Again, this is Vulkan. Can you actually do that in your app? Yes, you can. You violated the validation rules. You're going to get undefined behavior. The things that get included into the command buffers are all the different VK command commands. They operate in the command buffer. They are the recording commands. Some of them set state in the command buffer, and some of them are actions in the command buffer. So let's go a little bit of detail into the primary and secondary command buffers. The fundamental thing that's different between the two is in primary command buffers, I can do my render pass commands, which are both begin render pass, next subpass, and end render pass. I can do execute commands to secondary command buffers. Submission commands can only be submitted. These primary buffers can only be submitted to the queues, but they can also call secondary command buffers. Secondary command buffers, on the other hand, you can't put any render pass commands. In other words, you have to have the primary command begin the render pass, and then within that render pass, you can execute multiple secondary command buffers, but you can't have that secondary command buffer begin a render pass, end a render pass, or set a next pass. You also can't do an execute command within the secondary buffers, because then we'd have tertiary buffers and quaternary buffers. I think I did that wrong, but you know what I mean. It's not hierarchical. You've got two levels of command buffers in Vulkan. And of course, you can not submit these secondary command buffers. They can only be executed from a primary command buffer. So submitting. You submit them to a queue. This is, again, another one of these places where you're ThreadSafe on an individual queue. So I can submit it to the queue. If I submit multiple things simultaneously to the queue from multiple threads, you've had a validation error, undefined behavior. What you can also do with the submission is set a bunch of semaphores to wait on, set a bunch of semaphores to signal, and one fence that fires off and sets after all the command buffers that you submitted have completed execution. Want to caution you here. You want to use the semaphores for things that you need to have synchronization between the command buffers that you're submitting. But don't overuse them. You're going to be bubbling up your graphics pipe like crazy if you're waiting for stuff that you don't need to complete. The similar sort of thing is if you don't need a fence on this submission, don't put it on this submission. Put it on a subsequent submission. That'll be fine. Another thing for it is how much work should you submit in an individual queue submit. You'd like to move this out of your inner loop. You don't want to have, for every one of the command buffers I'm submitting, submit one command buffer, repeat, repeat, repeat. Gather them together and do relatively large batches of work in each one of the submission. How much is a relatively large batch of work? Well, if you've already gathered them all together and you're not taking a lot of time to gather all these command buffers together, then a large number is just perfectly fine. But if you're spending a significant number of wall clock time trying to gather all your command buffers, meanwhile, we're waiting around for you to please tell me what to do next. So there's this balancing act between I want to give you enough work, but I don't want to wait so long to gather up too much work. So you'll have to do some testing to figure out what the right kind of balance is between enough work and not too much work. So let's go into the beginning of the command buffer. Fundamentally, a command buffer is conceptually this little tiny state object out there. And you start out with no state defined after the beginning of the begin. So I'm showing you just the stuff necessary for compute dispatches right now. So you can bind, the bind state, the set state, and push constant states are all undefined at the beginning of recording a command buffer. So once I bind some state, bind descriptor sets, bind pipelines, whatever else I'm going to be binding to this, now that state is defined. I can then go off and use a command that consumes that state, which is, in this case, a command dispatch. I'm showing this with a hatched area saying the sets and the push constants are not used by this current dispatch, so who cares if there's no state? You only need to say set the state that you're actually using in the dispatch command. And that's the thing to think about it. What state do I need to have completely defined when I dispatch? And that's the state you have to have defined, and no more. I can then push some constants up and do a couple more dispatches that actually consume those push constants. Then I could do a secondary command buffer execution. The state of the command buffer resets to undefined. When I return back from that execute, I don't know what the state of the command buffer is anymore. So then I have to go and bind and push constants and maybe do a couple more dispatches all over again. Execute again, undefines the state, and so on and so forth until you end up to the end command buffer when finally now all that state that you've set in there is completely well-defined within that command buffer, but it doesn't bleed out to any other command buffer anywhere else in the world. Got it? The secondary command buffers, we're only talking about the compute case again. So bind, set, and push constants. And then you can go and do things like bind the objects, dispatch, bind some more objects, dispatch a bunch of stuff, set some push constants, dispatch, and finally come along in the secondary one. When you've done executing the command buffer, the secondary command buffer, none of that state bleeds back up to the primary command buffer. So again, completely self-contained state within that small area. So now let's talk about the render passes and the subpasses. First, again, we're going to come around to creating these objects. And the render pass, when you create it, you're going to have an attachment count telling me how many things I'm going to be using that are effectively, one way to think about it is things that I'm going to be writing to during the render pass. And for everything that you're going to be writing to with the frame buffer writes, you're going to end up creating an attachment for that. Also, you need to create attachments for things that you might want to preserve between subpasses. And this is where you're also going to come in with your dependency count and the dependencies between the subpasses. Jeff mentioned those earlier on today. So the attachments. So Graham mentioned before that the memory might alias. You can perfectly well go off in Vulkan and bind memory from multiple different places to different objects, or the same memory to different objects, and end up aliasing the object's memory to one another. By default, we assume that all the attachments do not alias with one another. So if you're doing that, you have to set this bit. Another way that they alias, if you end up using the one attachment in multiple ways in the pipeline simultaneously during the render pass. One time as a RGBA 8 frame buffer and another time as an R32 frame buffer, then that may alias. And you need to be able to reset. You need to set that bit. And we need to be told what the format of the attachments and what the samples of the attachments are. And the other thing that you're going to be telling us is what you want me to do with all these attachments. And the best way to think about this is, what do you want me to do with the attachments when I first use the attachment in a subpass? And what do you want me to do with the attachments when I last use a attachment in a subpass? For the first used ones, we need to know what you want to have loaded into that attachment. And either you want to load something into it, maybe you want to clear something, or maybe you don't care because you know you're going to completely cover everything with your skybox in the background. Please tell the truth there again. Huge wins on efficiency for telling us correctly that you don't care or that you're going to clear this buffer right off the get-go. And the same sort of thing on the store. Tell us what you need to store, and tell us you don't care if you don't need to store. And then I'm going to skip over the layouts. They're just a little bit of a kind of a, Jeff mentioned earlier today, some people use the layouts, some people are kind of ignoring the layouts. They're telling you where in the pipeline you would like to have this attachment attached and be optimal for during the render pass. Go into details with that with going into the spec. So the subpass description. A subpass, every render pass has to have at least one subpass, so subpass 0. But you can also have multiple subpasses, so 0, 1, 2, 3, and so on and so forth. They'll all have a pipeline bind point for those passes. And they'll end up having to be, because the only thing that we allow inside a render pass is graphics commands, you have to bind to the graphics pipeline bind point. Input attachment point count tells me how many attachments I am using in this current subpass. And it might be a subset of the entirety of the attachments of the frame buffer. How many are input attachments? Those are inputs that come into the fragment shader as previously rendered from the earlier pass. And this is where you get the 1 pixel to 1 pixel coherence. I've written this in a prior pass. I can see my own pixels data on the subsequent subpass, and that's all I can see with the input attachments. So how many of those are you reading in right now? The color attachment count is how many things you're going to be writing to this pass. The resolve attachments are which one of those color attachments would you like to have resolved at the end of this pass. Either all of them or none of them, basically. And then the depth stencil attachment is where you put your depth stencil buffer. And then the other one is the preserve attachments. Let's say I'm not using an attachment at all in this subpass, but I need to preserve the contents of that attachment. You have to put it into the preserve attachments. If you don't remember to preserve it, the contents of the buffer are undefined. They'll be undefined from that subpass to any higher subpass. You've lost it. You can't get it back. It's gone. Now, the render pass dependencies. So you have the source subpass telling you which original subpass I'm dependent on. The destination subpass, which one am I that has the dependency. And the stage masks tell you where in the pipeline you'd like to have the dependency be done on. And then finally, the dependency flags, which tell you what kind of dependency you have. For things like the input buffers, if you're moving something from an output buffer, a color buffer attachment, to an input attachment, the by region bit is almost a no-brainer to put on for that dependency between the two subpasses for that attachment. If you have other resources that you're going to be consuming in a subsequent subpass, but you know that that resource is only addressed as if it was in the frame buffer, by that pixel, then you can also set that region by dependency bit. And this is helpful for not just tilers. I'll be blunt. The dependencies and the store ops and the load ops and the by region stuff can all end up being used by multiple different implementations. There's a lot of different optimizations that we can do across direct renderers and tilers to be able to say, okay, I know that given this restriction, there are some things I can do more efficiently than if I don't know that you have this nice little quality to this attachment. So let's give an example in concrete terms. Please don't ever actually make a shader pass look like this. The first pass just renders the background, and in fact, in this particular subpass, it cleared it to green. The second subpass is the surface shader. The third subpass does the ambient light pass. The third subpass does the specular pass, and then the final one does surface times ambient plus specular over the background. So I set the dependencies. Source, Jeff and I think differently about which way the arrow of dependency goes. Mine goes towards the source, away from the destination. He had his arrows going from the source to the destination. So subpass 0 and subpass 1, 2, and 3, they're not dependent on each other. Subpass 1, 2, and 3 are not dependent on each other. 2 and 3 are not dependent on one another. But 4 is dependent on 0, 1, 2, and 3. So work can start proceeding on subpass 1 prior to subpass 0 actually being complete. All of these commands are issued in order but might complete out of order. So by having these dependencies there, I'm saying go right ahead and don't wait for this stuff to go. There's no collision on this stuff. So all of subclass 0, 1, 2, and 3 could even possibly have been reordered in interesting different ways conceptually. They're all started in order 0, 1, 2, and 3, but they might complete in completely different orders. And then the subtask finally pulls them all together. That's the only time that you've got to actually wait for all the prior contents to be done. In this case, because I've got such a somewhat forced example, all of these dependencies are by region. I did basically the classic movie visualization of what are all the layers that I'm compositing together. So all of these dependencies are by the region. We could begin the render pass, do a next render pass, and end the render pass to get us through the different render passes. Another thing is that when you begin a render pass, you tell me, a subpass, you tell me whether or not the next subpass is, the render pass subpass contents are in line in that they're all in the primary command buffer or secondary command buffers. So I can't, within a single subpass, mix a few things in the primary command buffer, go off, execute a couple of secondary command buffers, and come back up to the primary one. I'm promising either everything's going to be in the primary command buffer or everything's going to be executing secondary command buffers. And then the other thing that goes along with the render passes is the frame buffer. We would like you to so you can create a frame buffer from a render pass or a render pass that's compatible with the existing render pass. Strongly urge you to try to create the frame buffers for the render pass that you're actually going to be executing. There's some huge potential wins there. You tell me how much attachment count you have, how many attachments, and the width, height, and the layers. The other warning is don't go with an uber frame buffer where you have huge numbers of attachments that sometimes you're only going to be pulling a few things out of. Try to segregate your frame buffers into rational size frame buffers that have a limited number of attachments in there that you're going to be using for lots of different kinds of render passes, and make specialized render pass frame buffers for those render passes. And then in the command buffers, the other thing that I haven't talked about yet, and I'll be finishing off pretty much what's happening with these things, is some of the commands could go both inside and outside of the render pass. Some of them can only go inside, and some of them can only go outside. So the binds and the sets can go inside of both of them. Draws can only go inside, and computes can only go outside. All the copy-like commands, the copies, updates, clears, blitz, and resolves, have to go outside of a render pass. One exception to all that is the clear attachments. You can clear an attachment inside the render pass. Conceptually, you're clearing just that one pixel in that render pass. Set events and reset events have to go outside of the command buffer, render pass, but wait events and pipeline barriers can go in both. However, you have to tell us that you have a self-dependency if it's within a single render pass. You have to tell us that you've got a self-dependency before you can go off and use those. And there are some quirks on what kind of waiting and pipeline barriers you can have in. The barrier stuff is coming up in a moment. Again, reset query pool, Graham mentioned these, and the copy query pool results have to go outside of the render passes. And the begin, end, and write timestamp can go both inside and outside of render passes. Push constants could go both. And then finally, the obvious thing is you could begin a render pass outside the render pass. You can do next subpass and end a render pass inside, and you can execute in both. Putting it all together, here's a primary command buffer executing and undefining and redefining its state. And then here's a secondary command buffer that's being executed from that primary command buffer within the render passes. So thank you very much. I think it's time for a couple of brief questions.
You've got time for one.
OK.
No questions.
All right,
Okay,
thank you.
I need to talk into your shirt.
Oh.
No, we're not that good friends. So thank you, Bill. I told a lie. It's a little too early to take a break. We're going to let Tobias talk. We are still ahead of schedule, so we'll take a 10-minute break after he speaks. He's speaking for half an hour. Okay, Tobias?
How am I? Where are we? What have you done, Bill? Are we?
We should be. No, it's.
Oh, right, OK. It was just further
There
down.
we go.
You had some extra
All right.
slides. OK.
All right.
Hi, I'm Tobias. I'm from Imagination. So I'm going to talk to you a bit about synchronization. Bill sort of touched on some of it, but I'll go into a bit more detail about them. So keeping your GPU fed without getting better. What do I mean by that? Well, you have a ton of delicious draw calls. You're an app developer, you've got draw calls, right? Your GPU, it's hungry. It really wants to eat them. And so if you keep it fed at all times, it's going to produce delicious, just wonderful pixels. But you really don't want to get bitten. I mean, those teeth are horrible looking, with a little less weirdness to it. What I mean by that is that you kind of want to keep it going. You want to have a source of draw calls at all times. You don't want to have to let your GPU stall while you're giving it work. And certain things you ask the GPU to do may have stalls inside themselves, like if you have some memory latency where you're trying to fetch data or such. Draw calls, in fact, have a lot of different tasks, and they can be pipelined. So, simple example of the CPU and the GPU. If you are being fairly naive and you have a bunch of draw calls, you submit them to the GPU, and then you just sort of wait for them to come back. Then, whilst you're waiting on the CPU for the GPU to finish, you're not doing anything there. And while the GPU is waiting for the CPU to generate draw calls, you've got nothing going on there. That's not a great situation. So if you can make them pipelined and get them working at the same time, whilst one's consuming the previous frame, the CPU's working on the next frame, you can do more in the same time, and there's no weird idle time that you have to worry about. Similarly, within individual tasks on the GPU, you kind of want to have overlap between all the various parts of that GPU at once so that they can hide latency and other stalls that might happen. So I can easily replace CPU and GPU with fragment vertex, and you'll get a very similar thing. It's a little more complicated. There's more shared resources. In particular, the shading processor is usually shared. But there's still benefits to doing this kind of thing. And what do I mean by not getting bitten? So the GPU is constantly looking at lots of different resources while you're rendering. And if you touch any of that stuff while it's doing it, weird stuff can happen. You don't want to change a resource while it's looking at it because you'll get bum data. And if you delete something, then you're likely to get page faults. And the effects of this can range from anything from simple tearing, or you get complete image corruption, or everything might explode and you'll get polygon shrapnel everywhere. No one wants that. So I'm sorry, that's it. That's the fun bit over. Now back onto the serious stuff. So some terminology, an execution dependency. So that is effectively saying this task is going to wait on this other task. It's fairly straightforward. And all synchronization primitives express these very clearly. Then you've also got this idea of a memory barrier. This is oh, I thought I'd removed that. Never mind. Ignore the first sub-bullet point. The basic premise behind that is it flushes, invalidates caches, and it tells the GPU when and where you're going to be accessing data from. And finally, then there's memory dependency, which is basically a combination of the two. A memory barrier is effectively a task, and a memory dependency is an execution dependency that waits on a memory barrier. So there's sort of three types of explicit synchronization with Vulkan. You'll notice that I've grouped three of them together because they all broadly have similar uses. Pipeline barriers, events, and subpass dependencies are all within a queue, within a command buffer, in fact, and they all have very explicit memory dependencies that will give you a lot of detail and control over what you do with them. Semaphores operate between and sort of within queues as well. Their primary use is to synchronize different queues, although you can use them within a single queue if you need to. And finally, fences, which allow you to do synchronize the CPU to queue operations. So the first set of that, pipeline barriers. So these are quite in-depth. They're very fine-grained in the fact that they allow you to express a lot of detail. You have to say exactly which pipeline stages in your GPU you're actually waiting on and where you're waiting from. So source stage mask will tell you what task I'm waiting on. So I might be waiting on some earlier vertex processing. And then desk stage mask, you'll say when you're waiting at. So you might be waiting at the fragment stage or another vertex stage, et cetera, et cetera. And it also encompasses a bunch of memory barriers to execute. The important thing about pipeline barriers, they're a single point in time. They effectively synchronize everything you've told it before the pipeline barrier with everything after the barrier that you've told it about. And it's a single command function that goes in the command buffer. Events are kind of similar. They express almost exactly the same type of detail. The main difference is that they operate over a range instead of being a point thing. So you have to say when it starts waiting and when it actually finishes waiting, effectively. You have to use a command set event, which effectively triggers it and says at the point this executes, the event will be triggered. And then you have a separate wait command, which at the point that executes will finalize that dependency. They also have CPU interaction, which is quite useful. There's no explicit CPU wait because we don't really want you waiting on the CPU, so you can query the status. And you can't do memory barriers if you're waiting on the CPU because it doesn't really make sense. But that is a thing you can do. However, bit of a warning, if you submit a piece of work to the GPU that waits on an event and you don't almost immediately submit a set event somewhere, there's a good chance that an OS may actually time you out, and who knows what's going to happen with that data. It's basically undefined behavior. It's not a super common use case, but it's something to be aware of if you do find yourself needing to use it. So memory barriers, I sort of skimmed over them. There's three types. There's the global memory barrier, which is effectively any memory-backed resource you've got in flight at the moment. Buffer and image barriers both define single resources and what you're going to do with them. So global memory barriers, again, it's all memory used by any of the source stages you ask for, and effectively flushes like everything in a cache that would be relevant to that stage. And you mainly want to use it when many or most of your resources are going to be transitioning in the same way. It sort of saves on having to ask the GPU to individually flush different bits of the cache at the same time. But there's a balance to strike, and you may need to do some tuning. Buffer barriers, similar sort of thing, but instead of all the memory, it's a single buffer, or rather a range within a single buffer. It doesn't have to be the entire buffer. Bearing in mind that a buffer may be attached to multiple memory objects in the background, but that's all defined by the application. The differences really are that you can, if you have multiple queues in the system, you can tell it which queue is taking ownership of a buffer, and you can also say which, and you can say which range of the buffer you can do. Similarly, with image barriers, they also have the access stages, and they have the queue ownership as well. And they have this idea of the layout as well, which tells you how I'm using this particular image at this point in time and how I was using it. So I skimmed over a big bullet point on all the other ones as well, but I'll just talk about it here. You have to know what you were doing with it before. In most cases, this can be statically determined. You can often code it as a hard constant. It doesn't necessarily have to be tracked by the driver, by the application. In fact, generally speaking, you shouldn't be tracking individual resources. You should batch them if you have to, or just implicitly know, hopefully. And one thing to say on layouts is that if you use them appropriately, if you tell them exactly what uses you want to have it with, and you've actually said the image, I'm using these usage cases, it can allow certain implementations to use compression schemes under the hood, so that you can use less bandwidth and less memory allocation in some cases as well. And so it's quite important to actually use the correct layout to actually achieve this. If you just stick yourself in general all the time, you're unlikely to get this unless some hardware happens to support compression for all types of access, which is not hugely likely. Now, Bill did mention subpass dependencies. And there's another bullet point here that hasn't been updated. Never mind. So again, it's similar sort of info to a pipeline barrier in the sense that stuff happens before, stuff happens after it. They're used in different ways, as Bill explained when he talked about render passes, and they are explicitly between two render passes in the sort of graph-like structure we saw before. I don't know how to talk to this bullet now. Sorry. The effective point of these dependencies is to say, I have resources that I'm using in this subpass, and I'm going to be using in the next one. And that includes all the input attachments you may be using as to read from previous previous subpasses, and it may also include global resources as well that you've used in a previous subpass. And as Bill mentioned, there's this idea of pixel local dependencies. So if you're accessing a resource only at the same location from multiple passes, then you can use this dependency by region. And again, Bill vaguely mentioned this, the idea of self-dependency. So subpasses somewhat unintuitively can wait on themselves. It doesn't actually mean exactly I'm waiting on myself, because that would be nonsense. What it means is that you've put a pipeline barrier in the subpass, and within that subpass there's a dependency. Now, there are a lot of rules on these dependencies you can put inside the subpass. The main key one is that you can only go forward with pipeline stages. You can't wait, say, in the vertex stage for a fragment stage operation from the previous subpass. You can only do it the other way around. You have to wait at a later stage or the same stage. And this mostly is to avoid a significant number of pipeline bubbles that could otherwise occur. Particularly on tilers, for instance, you may end up having to split your rasterization workload, which requires loading and storing a lot of data from the chip. But even on a direct renderer, you'll find that there are pipelining issues if you don't have this. And the other one that you can do is an external dependency. So to do this, you can actually, there's a special value, which for some reason I haven't got on my slide, which you set in the source and or destination subpass, which is subpass external. And if you do that, it means you can either are waiting on a previous task to execute, in which case you can put a command wait event inside your subpass, which will wait on that external task. Or you could be saying that actually some external task later will be waiting on this, and it's a similar thing, then you'll put a barrier later. So that's sort of, the reason I grouped all those together was basically because they all operate on the same ground together. They're within command buffers. They have very explicit detail about what's depending on what, and how the memory is accessed, et cetera, and you pretty much find you're always going to be using some amount of these. Semaphores are a lot more coarse-grained. So you use them to synchronize queues, as I said, and if you've only got one queue, you don't need them, but you can use them. Within a submission to the GPU, you can have a number of different batches of work, which is going to be a set of command buffers or a set of other operations that happen on the queue. And each of those batches can be associated with some semaphores it waits on and some semaphores it triggers. They do make some implicit memory guarantees, so they don't have an explicit set of memory barriers like the events and pipeline barriers do. Instead, what they have is they make the guarantee that any writes or side effects done by the things you've submitted will be visible to any future queue work. They won't be visible to the host, but they will be visible to future queue work. Fences are used to synchronize from any given queue back to the CPU. So these, again, very coarse-grained. They're actually more coarse-grained than the semaphores are. Rather than per batch, it's actually per individual submit command. And you're not expected to be doing multiple submits per frame. You usually want to do one because they're not completely free. They can be cheap, but it sort of depends on the OS. But ideally, you should really only be doing one. Again, they make the same sort of implicit memory guarantees as a semaphore does, but that's not. It may or may not be useful to you. The interesting thing is, the interesting use case for them is to check if you're doing something like multi-buffering your resources and you've got multiple frames in flight, then what you can do is you can use a fence to determine when that frame has ended and you're free to use your resources again. However, as I've said, it's not guaranteed to be visible to the host at that time, which you may want in some cases. So you actually have to have events in your command buffers as well to determine that they are going to be host visible after this. There's a couple other commands that ensure execution completes, which are very, very heavyweight. There's queue wait idle, which basically does the same thing as signaling a fence on a queue and then waiting for that queue, for that fence. And then there's device wait idle, which is effectively every queue on that device I'll wait for in the same way as queue wait idle. They're not something you should be using every frame because they'll introduce that stall that I pointed out in the first set of graphs I had, where you've got your CPU waiting for GPU and whatever else. They're mostly useful when you're doing sort of shutdown things or if you need, for whatever reason, to flush the pipeline. But the idea is that when you're shutting down, you can use that and you can say, right, all my resources are done with, the GPU is not touching anything more, I can now delete everything safely. But it does not, again, mean that you necessarily have all the data written, so you still have to manually do that if you need anything written at the end of rendering. So the guidelines to this, I think people have said this already today. You need to be very careful to specify what you need, and synchronization in particular is very key for that. If you don't specify enough synchronization, if you specify too much synchronization, you risk starving your GPU and getting those sort of pipeline bubbles. If you miss any, then your GPU is going to bite you, and basically all that nasty stuff's going to happen. Just remember the teeth. If you can think about image layouts, try and, again, specify exactly what you're doing with it. Don't just use general. And if you're lucky, or if your hardware supports it, you'll get some nice frame buffer compression and avoid, or image compression, and avoid an amount of bandwidth you may have otherwise had to incur. Now, you do get different behavior depending on implementation. Some of them will ignore the layouts, some of them will ignore some or all barriers, and some of them may ignore other bits and bobs, or they may, conversely, really rely heavily on them. It's also worth pointing out the drivers are still being brought up to speed, so there's optimizations to be done. And those optimizations are going to rely heavily on the information you provide them. So you may find that an earlier driver revision or a different driver revision, it works, and because you've got your synchronization wrong, suddenly it stops working when you update your driver. And it's not because we're out of spec, it's because we're suddenly using this information you're providing. So you've got to be very careful to use it. The Lunagy and Khronos validation tools, really, you should rely heavily on those for them for these. I don't know that they catch everything right now, but obviously we'll be working on bringing it up. And so in summary, keep your GPU fed without getting bitten. I think I've gone massively under time, but that's fine. You can all have a break. Does anyone have any questions? Okay.
Yeah. Just rip it off.
Oh, yes.
Be brutal.
Oh, no.
No, you're good. Just don't move. Okay. Tobias does talk very, very fast, so we're now well ahead of schedule. We're going to take a 15-minute break, which means that we will resume at 5 minutes after 4. Okay, so coffee, as I said, go outside and straight back. There is some water there. I hope they've brought more things. So Alon will resume in...
I'll make sure I'm oversharing.
Okay, all right, thanks. Thank you, Tobias.